Okay, continuing on, we just finished with the tcat auto block and running AFNI in the results directory, looking at the PB00 datasets, and then the output of radio correlate in the radcore PB00.tcat directory. So now let's just continue on. The next step in the proc script is another automatic processing block called outcount. In this block, we look for outliers. So we're not actually doing any modification of the EPI data. You see the bottom of the processing block here. I'll try to scroll up just, it doesn't quite fit on the screen. See, let me. So, but let's put most of the outcount block here, and we're looking for outliers here. And we're not going to actually modify the EPI data. We're just going to make note of anything that we're not happy with. So for each run, we're going to run 3DT outcount with dash automask. What dash automask does is it looks for higher intensity contiguous block of voxels. So we have a blob in the middle of the data set. If I go back to my AFNI window, here's the AFNI window. I'm not looking at the right time series, am I? I'll just jump to again. There we go. If you consider this data set as if you consider this data set kind of from a high level, it's the higher intensity voxels basically form a big blob in the middle of the volume. So that's what 3DT, that's what the automask option does for many programs actually, is it tries to locate this blob of higher intensity voxels, and it turns that into a mask. So let me make a little comment here. As you start getting too many windows floating about, you may lose things. So for example, where is the coronal image? If I want to find that, I can just click on the coronal image button and it will raise that. More useful perhaps is sometimes raising it isn't even enough. If you right click on image, it brings the image window over to this location. So that's helpful. Also, just to lose something else, now where's my AFNI window? Well, if I go to like one of the image windows, they have the display button in the lower left corner. If you right click on that, it raises the corresponding AFNI controller window. So that's one helpful way to find things. So I'll just click on all of these to raise them. But we don't care about the sagittal or coronal windows, so I'll do Q to quickly close them. And back to the proc script here. So now we're looking for outliers in the automask, and we want to look for the fraction of outliers within the automask, but we'll do with polynomial polar 3 detrending. So we'll basically look for whatever is the best fit cubic trend to that single run. This is a single run at a time. For each run we're doing this. So the input is PB00 for one of the runs at a time, say run 1. We'll fit a cubic polynomial to the data, Legendre polynomials, and from that best fit, we're looking at how far the values are deviating from it. So if you picture a cubic trend through here, the deviation is actually pretty big from there. However, what it considers an outlier is a voxel whose deviation is more than typical. So just for kicks, we can practice running help. 3DT outcount. Whoops, 3DT outcount. Oh my goodness, 3DT outcount dash help, I do less. And here's the help, and you can look for the definition of outliers. It's right near the top here. Outliers are defined as follows, and basically you're getting the median absolute deviation from this trend. So we've got, for whatever cubic trend fits here, just pretend it's a straight line. What's the median absolute deviation? So at each time point, how far do we deviate? and then overall 150 time points, what's the median, the 50 percentile deviation. So that's what we'll consider normal. Note that a voxel that has bigger spikes in it is going to have a higher median absolute deviation. So outliers are relative to however much the data values are fluctuating to begin with. So then each time series voxels that are far away are, if you're blah blah blah, I think it's basically for typical data, if you're like 3.5 median times the median absolute deviation from the trend, then you're considered far away. So like this should be a spike. This should be a spike. This should be a spike. This might not have any spikes. This might not have any spikes. So that gives you some idea of how it views this. I'll cue to quit here. And so what we're doing in our 3DT outcount command is now we know for a single voxel time series, we have an idea of what is a spike and what is not. No, 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 yes, no, 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 no. So thinking from a volume perspective now, one time point at a time, within each time point volume, what fraction of the masked voxels, so presumably of the brain, what fraction of the brain has an outlier? And if that fraction is big, we'll say that time point is an outlier. And remember, in our AFNI proc command, we actually specified censoring on outliers whenever the fraction is greater than 0.5. So we're looking at these numbers, and anytime the outlier fraction exceeds 0.05, then we'll say that time point should be censored. So we're actually making censor files right off the bat here. If you're not censoring, that's okay. Then it just won't create this censor file, but it will still run to the outcount stuff and just look for outliers, even if you're not censoring. So let's just note here, it's producing these outcount files. So in our directory that we typed ls in, outcount, run 1, 2, and 3, and then we have this outcount underscore r all. That's just a catnated version of them right here. So here's a wildcard r star.1d. If I do ls-l on r star outcount r star.1d, it lists those three files. Or just to be interesting, if I echo that, then they're on one command. So this command here, cat, it's just going to, cat is short for catnate, it's just going to dump the text files, and three of them, so one by one, and then it's going to redirect the output to another text file. So this text file is just across all three runs. And what do these things look like? Well, if we look at this one file, outcount.run1.1d, it's just a single list of numbers. And that is, at each time point, what's the fraction of the brain that has outliers? So this is 0.4% at time point 0, etc. And we can page down and get to the end. Of course, you don't tend to look at it like this. You tend to use 1D plot for something like this. If we do 1D plot on this file, we get a time series plot, and lo and behold, we seem to have some sort of big fluctuation at time point 42, which is our motion, our fake motion spike. And you can see basically 45% of the brain, of the masked, estimated brain mask voxels are viewed as outliers there. The rest of it is pretty smooth, pretty flat. 0.05 is our sensor limit. So if I draw a horizontal line here, anything that hits 0.5 is going to be censored, and that seems to only happen right at this spike. The rest of it is very flat. That's one reason I like these outlier curves, is they're not so noisy. It's fairly clear when something is happening and when something is not happening. And then if we, I'll leave this one up on the screen briefly. Just to leap back into Unix land a little bit, I can't type any commands here because 1D plot owns the shell here. It's running and I can't do anything until it's done. So if I want to, I can type Control Z. That's like Z. Well, you see the Z here. Control Z will suspend that. Now I can type commands in this terminal window. However, this window is no longer doing stuff. There's not much for it to do, but for example, if I try to quit out of it, I can't yet do it because it's not an active window, that's a suspended process. So if I type jobs, I can see that process 1 is suspended, and that's the 1D plot. But if I put it in the background, now it's active again. And it's Control Z and BG, you can see the shell is telling you it's as if we had put an ampersand after it in the first place. And at jobs again, you see it's running. It's not suspended. So anyway, that process is still going now. So if I 1D plot again, I can do outcount _r all, and I can see all 3 runs together. So in case we, for some reason, care about that, there's how they somewhat line up. So it looks like we'll do some outlier censoring here as well. Okay, so this is just a longer version that spans all 3 runs, and this one is just clearly run 1. I'll do Q to quit those things. Jobs, nothing running. So now that we've viewed our outliers, remember one other special thing about the AFNI proc command. In the parent directory, remember this is our AFNI proc command. If I just cat that file again, remember one of our options was -valreg align to min outlier. So this is a very useful option here. Again, we would like to align our EPI volumes to a single volume that isn't filled with motion. Motion can mess up a handful of slices or the whole volume, basically. So we'd rather get a volume that doesn't have much motion in it. And so what we ask AFNI proc to do is, in the proc script, find the volume with the minimum outlier fraction, and let's use that as our registration base. And because we asked to do that, down here at the bottom of the outlier block, we actually we look at the outliers across all the runs, and we find the argument of the minimum value. So basically we're looking for the time point that has a minimum outlier, and then based on converting that into the run index and a local time index, we get a run index and a time index, and we save those in variables, and we echo min outlier, and we pipe it through t_out min outlier. So here I can actually cat out min outlier. That's a text file, and we see it's run 3 time point 24. That's one of our out files here. And just to see that in a different way again, remember in the parent directory we have this output.proc.ft file that has all the text output that went across the terminal window. If I do less on that, it's in the parent directory, less on that, we can view it, and you don't have to do this, I'll just show you, but I'll search for min outlier in here. Searching is done with a regular, like a directory style, Unix directory style / min outlier, enter. And so I find where in the script that appears, and here we go. Run 3 time point 24. So that's right after running the 3D tstat and the 1D tool commands to get those numbers. So that's the volume we're going to extract to use for our registration base. And you see it in the proc script. We'll save these variables, and later on, we don't actually extract it now, but later on we'll extract it once we're ready to start registering our EPI data. So, having said that, let's actually get back to the AFNI windows and start looking at the next processing block. So we're not going to extract this here again. We've made note of which volume we care about, but we don't actually have the volume created yet because we're going to wait till we run 3D tshift first. We're going to do everything up until registration starts before we extract the volume that we care about. So the next processing block is the tshift one, where we run 3D tshift, and this is to do slice timing correction. So remember, when we acquired the data, we acquired the slices I to S. These are axial slices, the inferior to superior direction, but in an interleaved fashion. So we collected slice 0, 2, 4, 6, 8 up to slice 32 at the top, and then we went back half a TR later now and started acquiring slices 1, 3, 5, 7, 9, 11, etc. up to 31. So that's how we spent the 2 seconds acquiring 33 slices for this one volume. But so you know the timing of these slices varies across the TR over that 2 seconds. So we're at time index 0 here. You can see index 0. Well, I don't know if you can read this index equals 0 here, but same thing. The time is at t equals 1.333 seconds into the TR. Well, this is the absolute time from the beginning of the run, but since we're within the first TR, that also is relative to the 2 second TR. So we're a little bit more than halfway through the slices. We're actually basically 2/3 of the way through the 33 slices. We've collected, the first half of them is 34 over 2 is 17 even slices, and then 16 odd ones. So, we've gotten about 28 slices acquired at this point. So each slice, if we go down, for example, to slice 0, you see slice 0 is acquired at time 0. Slice 1 is at time 1.030, so that's half a TR later. So after acquiring slice 0, we didn't acquire slice 1, we acquired slice 2. That's at time 0.0606. Slice 4 is at time 0.1212, etc. Then at slice 32, we're like half a TR into it. I guess I can middle click here. We're at time point 9696. And then we go back and acquire slice 1. Again, you saw that's just over halfway through the TR, 0.1030, etc. So anyway, we don't want adjacent slices to have data acquisition times that are half a TR apart, and we don't want data across the volume to be basically a full TR apart. So the purpose of the 3D tshift operation is to interpolate the data and shift it so it is as if we acquired the volume, the entire volume, at slice index 0, at the beginning of the TR. Just to note what this looks like over time, let me jump back to slice 11, say. That's where we were at. And so we're at time 1.33. If I jump through time here, if I put my cursor over the graph window and hit the right arrow or the greater than key, you see we jump time equals 1.33, time equals 3.33, 5.33, 7.33. So at each time point jump, we're moving 2 seconds later on. So the TR, the time between volumes, is still 2 seconds. There's a 2 second difference. but we're always 1.33 seconds into the TR for all the voxels in slices 11. So I'll leap back to index 0 here. So 3D tshift is just going to interpolate along whatever curve of data you have and make it as if the entire volume was acquired at the beginning of the TR using quintic interpolation. We tend not to use Fourier interpolation, even though it's like mathematically elegant and all that, because Fourier interpolation causes spikes in the data, like these perhaps, to ring across time. So we would rather this spike just be a local artifact than to have it cause trouble everywhere. So we don't use Fourier interpolation. We're using just a polynomial interpolation. So let's look at the result of this. I'll close this window here, Q, and let's look at the result of the 3D tshift operation. So here's where I'm going to open a separate set of windows, a separate AFNI controller and a set of windows. This is controller A here on top, A in square brackets there. If I hit new in the main controller window, I'll open up a new controller window, and you see that this is window B. If I open up an image and a graph window, you see that these have B's on them as well. So make these kind of the same height. Quick comparison. So now we have controller A windows on top and B on bottom, and so we can compare before and after. So in the bottom controller, let's set our underlay up. Let's set our underlay to be the result of that tshift operation. So we'll set the underlay to be pb01.run1.tshift. And if you compare the time series between the bottom and the top, they're basically the same. You don't see a striking difference. There are subtle differences between them, but again, we're just interpolating across time, so the basic temporal pattern shouldn't be changing much. But if you look at, so on top we have index 0, the value is 1198 at time t equals 1.33. On the bottom, index is 0 at time t equals 0. Now it's as if we acquired the whole volume at the beginning of the TR. And if we scroll across slices here, you see t equals 0 in red on the bottom for all the slices. On the top ones, I guess I can watch the top graph window, you see the t is changing. So that's it. I'll jump back to where we were. That's the purpose of 3D tshift, just to do a little temporal interpolation, so that it's as if we acquire data at the beginning of the TR. We could interpolate to the middle of the TR as well. That's actually the default, but usually people set up their timing files with respect to the beginning of the TR, so that's why we default to that. But of course, as with most programs, you can provide your own options to override what this is doing. So let's take a break there, and we'll come back with the next step in another video.